This presentation explores how the Working Group 1 report of the IPCC addresses carbon dioxide removal. Carbon dioxide removal in this report is assessed in 2 chapters. Chapter 4, which is the chapter about future climate projections. And this chapter focuses on the climate response to carbon dioxide removal, or CDR, and the termination effects of CDR. Whereas chapter 5, which is the chapter on carbon and other biogeochemical cycles, looks specifically into the carbon cycle response to CDR and addresses aspects such as the effectiveness of CDR at drawing down atmospheric CO2, the asymmetry in the carbon cycle and temperature response to carbon dioxide emissions and removals, and the effect of specific CDR methods on climate and biogeochemical cycles. The figure to the left illustrates the response of atmosphere, land, and ocean carbon stores to 100 billion metric tons of carbon, which corresponds to about 370 billion metric tons of carbon dioxide removal from the atmosphere. And this figure illustrates that after the removal, the atmospheric carbon dioxide concentration declines very rapidly and then rebounds within a few years of the removal. And this rebound is due to loss of carbon dioxide from the land and from ocean carbon reservoirs. And this illustrates that only a fraction of the CO2 removed remains out of the atmosphere. This fraction of CO2 removed that remains out of the atmosphere is a measure of CDR effectiveness. And it is not a constant number, but it depends on the atmospheric CO2 concentration from which CDR is applied, and also on the magnitude of the carbon dioxide removal. So this is illustrated, for example, in this upper panel here, which shows the fraction of carbon dioxide that remains out of the atmosphere after removal as a function of the CO2 concentration from which carbon dioxide removal is applied. And what we see here is that as the CO2 concentration decreases, the fraction that remains out of the atmosphere, or in other words, the effectiveness of carbon dioxide removal decreases as the atmospheric CO2 concentration decreases. It also shows that there's a slight dependence on the magnitude of removal. So here these triangles indicate a smaller amount of removal, whereas these squares here indicate a larger amount of removal, indicating that the effectiveness decreases slightly with the amount of removal. The report also addresses the asymmetry in the carbon cycle response to CO2 emissions and removals. So this figure here shows the fraction of carbon dioxide emissions that remain in the atmosphere after an emission. So this is shown here to the left of this graph. And here to the right, it shows the fraction of CO2 removals that remain out of the atmosphere after a removal. And these different symbols, they indicate a range of Earth system models. And so what is shown here, that the fraction of CO2 emissions remaining in the atmosphere after an emission is larger than the fraction remaining out of the atmosphere after a removal, implying that CO2 emissions are more effective at raising atmospheric CO2 than CO2 removals are at lowering atmospheric CO2. And for these models shown in this figure, this asymmetry ranges from 2 to 9%. So the results presented so far were based on idealized model simulations, where it was assumed that carbon dioxide is removed from the atmosphere and permanently stored in the geologic reservoir. But another part of the chapter also assesses the effect of specific CDR methods on climate and biogeochemical cycles. So here, these different rows, they correspond to different CDR methods, which range from land-based methods such as afforestation, for example, or soil carbon sequestration, to ocean methods such as ocean iron fertilization or ocean alkalinization, and then to some more technological or engineered methods such as direct air capture and storage. And the core of the Working Group 1 assessment focuses on the biophysical effects of these methods. So biophysical effects are effects on evapotranspiration, for example, or on the reflectivity of the Earth's surface, which is referred to as albedo, which in turn affect the temperature at the surface, and on biogeochemical effects, which are related to emissions of greenhouse gases such as nitrous oxide and methane, for example, or in the ocean on effects such as ocean acidification. And it also assesses how these biogeochemical and biophysical effects then feed back on the carbon sequestration potential of each of these CDR methods. And then for completeness, we also show the sequestration potential of these CDR methods and potential co-benefits and trade-offs with other societal goals that are related to water quality or food supply, for example. And a detailed assessment of the sequestration potential and its co-benefits and trade-offs will be done by the Working Group 3 report. And really what this figure here illustrates is that all CDR methods have a range of side effects on biogeochemical and biophysical cycles that could either amplify or weaken the climate benefit of these CDR methods. In chapter 4, the climate effect of emission scenarios with net negative emissions is also assessed. So in this example here, the climate model responds to an idealized scenario with atmospheric CO2 concentration rising to 4 times CO2 and then declining back to pre-industrial levels as shown. And then these different curves here in the upper left panel, they show different climate variable. And what this figure here illustrates that the changes in these variables lags behind the decline in the atmospheric CO2 concentration that is induced by net negative CO2 emissions. And now some conclusions. CDR results in a drop in atmospheric carbon dioxide concentrations as intended, but not all of the CO2 removed remains out of the atmosphere, because the CO2 that is removed is partly replaced by release of CO2 from the land and the ocean. Also, the effectiveness of CDR at drawing down atmospheric CO2 is not constant, but decreases with decreasing atmospheric CO2 concentration from which CDR is applied and increasing amount of removal. The asymmetry in the carbon cycle response to CO2 emissions and removals implies that offsetting a CO2 emission with an equivalent CO2 removal could result in a different climate than avoiding the CO2 emission in the first place. And finally, most CDR methods have effects on climate and biogeochemical cycles that could either amplify or reduce the climate benefit of CO2 sequestration by CDR methods. Thank you.